All right, folks, we are back at section 4.23, studying discrete features. So what is this all about? We are looking at the classification problem. We're taking the generative approach to it. So we've been modeling the class conditional distributions and multiplying them by their class priors to get the joint distributions, and then trying to determine where the decision boundaries are for deciding whether a new data point belongs to one class or the other. And we found that based on, if we make particular assumptions on these class conditional distributions, then those decision boundaries are linear. We've looked at that so far for the case where these class conditional distributions, so the probability of a data point coming from a class, are Gaussian, will give us linear decision boundaries if we assume that all of the classes have the same covariance. So now we're going to look at other types of class conditional distributions that come up. For example, in this case, discrete features. We'll also cover in this video kind of the exponential family. It's kind of broadening the scope of it and seeing some conditions under which we'll get these linear decision boundaries. Okay, and it's a pretty short video. The topics covered are going to be pretty straightforward. There's a couple of points I want to make out while we're talking about the exponential family, but we'll get to that when we get there. Okay, so the whole idea is to see what is the joint. If you guys can see this, good. So what is the probability of x, the joint probability, which is the probability of x given ck times. And we're going to actually be looking at the logarithm of this, which is going to give us these terms. So for every data point, you're going to compute this joint probability of a data point coming from each class. And now the decision boundaries are going to be the locations in your data space where the probabilities for two classes, the top two classes, are equal. And if those individual probabilities are linear in your data, then the decision boundaries are also going to be linear in your data, because that's going to be the situations where the probability of you'll have situations where it's like the probability of something is going to be linear in x, and it's going to be equal to k prime, right? And so this whole situation is going to end up being something like xt is equal to some constant value. And so that's going to give a linear decision boundary. So the whole game is going to be trying to determine the conditions under which these kind of joint probabilities for your data and your class are going to be linear in your data. Okay. So let's do that. So we're going to look at a couple of examples. So the first examples we're going to look at are for discrete features, and then we'll, as I said, talk about the exponential family. Okay, so let's erase all of this stuff. And get on with it. Okay, let's move that over to the side. Okay, so now he says, let us now consider the case of discrete feature values xi. Okay, so we're going to be talking about these vectors x, and they're going to have, and in our case, we're going to be just dealing with a binary case. The extension will be obvious. So let's say x1, x2, all the way to xd, and each one of these is going to be 0 or 1. Okay, so like, for example, it's going to be like 0, 1, 0, 0, 1, so on. Okay, and there's d of them. Okay, so now it says, okay, so for discussing extensions of more general discrete features shortly. If there are d inputs, like what we have, then a general distribution would correspond to a table of 2 to the d numbers for each class containing 2 to the d minus 1 independent variables, because, well, the probabilities have to sum to 1, so 1 degree of freedom is gone. But the main thing is that there's going to be 2 to the d possible numbers, right? So if you want to specify, p of x given, let's say, class 1, well, you have to specify that for every single combination, right? And if there is d possible slots and there's 2 values each slot can take, well, you have to specify 2 to the d numbers, minus 1, to specify that probability distribution fully, just for one class. You have to do the same thing for every other class. So we're not going to do that. We're going to actually make a simplifying assumption, and we're going to make, and I think we've covered it already at some point before, we're going to make the naive Bayes assumption, right? So we're not going to say, we're essentially going to impose a dramatic simplification on the relationships between these elements. So we're going to say they can't quite be anything. The probability can't be quite anything. The probability is determined by looking at these values individually and kind of combining them. So the naive Bayes assumption says that the probability of, let's say, x given whatever class is actually going to equal to the probability of each of the elements from that class. So we're not going to look at kind of how whether like pairs of them are coactive or not. That's not going to matter. All that matters is what the class is, and that's going to determine the probability of each of the elements of that vector. Okay, so that's going to dramatically simplify our problem, because, for example, what would we have to specify? For each one of these elements, we're going to have to just specify two values, right? The probability of xi being 0 given the class, and probability of xy being 1 given the class, and that's it. Given those numbers, so just two values times, we've gone from something that's 2 to the d has been reduced to 2 times d, right? And that gives you per class. But again, this is a very, we've had to tremendously simplify our distribution. It might not actually capture our data, but for our purposes here, it's going to suffice. Okay, so we're going to make this naive Bayes assumption in which the feature values are treated as independent condition on the class, right? So we're going to throw away all dependencies. And just to make our life simple, condition on the class. Thus we have class conditional distributions of the form so and so, right? And so this is going to be, probability of, actually it's going to be, yeah, there we go, probability of xi given the class. And the probability of xi, so in this kind of Bernoulli type data, it's going to be, there's going to be a rate for each one of these dimensions. There's going to be, notice there's a k is for the class. So this is saying there's two things going on here. You're saying you have to specify the probabilities of each of these values, of each of the slots, and you have to specify them once for each class. So there's this is the this is going to be the slot index and the class index, right? So the probability of x will in general be different based on the classes, and that difference is going to come in through these rates. Okay, and so this is a probability saying, if xi is positive, if xi is 1, then the rate is going to be determined by mu ki, the probability is mu ki, and if xi is 0, it's going to be determined by 1 minus mu ki in this binary case. Okay, so that's just all where that comes from. And now aik, remember this is log p of x given ck times p of ck is this thing, right? And so you just compute the logarithms, the xi's come down, and you've got the class priors. So again, which are again linear functions of the input values, right? The xi is multiplying here, and the xi is multiplying there. For the case of k equals 2, yeah, you can kind of go back and jiggle it a different way, but this is the core point. And when you want to determine the boundaries between two classes, you just set these, ak of x equal ak prime of x, and that'll still be linear in x, and that will give you linear decision boundaries. Okay, so that's all there is. So the whole point is that even with discrete features, at least in this particular case, we also get, and it's I think it's a common case, we will also get these linear decision boundaries. Okay. It's also kind of interesting to see what they look like. So let's just go, this is going to be ln of mu ki over 1 minus mu ki plus, some ln of 1 minus mu ki. So, we're going to end up getting x transpose some weights, and the weights are going to be essentially the log odds of the positive value for each element. Okay, so that's going to be that. So it's going to be it's going to have a very similar form. It's going to be this linear in the data. It's going to give us linear decision boundaries. Okay, so that's this discrete features, and now we're going to kind of broaden. We're going to look at the exponential family, which captures discrete features, and will also capture the Gaussian case before, but yeah, with the caveat I'll point out as we go. Okay, so he says, as we have seen for both Gaussian distributed and discrete inputs, the posterior class probabilities are given by generalized linear models with logistic sigmoid or softmax class activation functions. So remember this, I think the general case is easier to work with. So you just have, exp a k of x divided by sum on k exp a k prime, let's say k prime of x. That was the probability of C of k given x, right? So we had the probability of the joint probability of it also was also going to be the posterior probability, because of the way things canceled out, of a particular class, and you normalize it by the probability of all the classes of each, but the summed probability of all the classes. So that was this kind of softmax. That was a softmax case. It says these are particular cases of a more general result obtained by assuming that the class conditional densities are members of the exponential family of distributions. Okay, so remember what that meant? So the exponential family had this form where this, let's say the probability distribution based on some parameters was a product of some term that just depended on the data point itself. Often that was just 1. And then some term that just depended just on the parameters. And then the way that the parameters interact with the data was in this exponential, there would be some function of x, so it doesn't have to be x itself, it could be x squared, whatever, interacting with the parameters, being weighted by the parameters, basically. There are other definitions, but that's the one we're going to use. Okay, so now he says, look, we're going to restrict our attention to the subclass of such distributions for which u of x equals x. Okay, so yeah, so the problem with this is that the Gaussian distribution that we're just talking about is not in this family. It's not going to matter because I'll tell you why it doesn't matter. But remember, for the Gaussian distribution, so let's just write that. So MVN not in that subfamily. Okay, right? Because remember, for the Gaussian, the u of x was x and then x squared, or some appropriate variant of that for matrix for vector value data. So we can't actually, this does work for the discrete case we talked about. It doesn't necessarily work for the multivariate normal is not in this particular family. It's not going to matter because because of the assumption that we made of the covariances being the same. So there's going to be, when you want to put the Gaussian distribution in this form, there will be a term that's like x transpose. And that's going to interact with the covariance term. But then when you come down to deciding these decision boundaries, all of those covariance terms will cancel out because we've assumed the covariances are the same. So the reason why we can kind of capture the Gaussian in this multivariate Gaussian in this framework when we're coming up with these decision boundaries is because we're assuming the covariances are the same, and then the kind of, let's say, the nonlinear terms in u of x kind of cancel out. Okay, so if you're kind of wondering why, if you're wondering about that, that's your answer. So then we make use of 2.236. This is the change of variables formula to introduce a scaling parameter s so that we can obtain the restricted set of exponential family class conditional densities of this form. I'm not exactly sure why he does this. I guess, to add some additional level of generality. So let's just highlight that. Okay, and notice all we've done, again, change of variables formula. So we've added some kind of scaling factor. So x has gone down to 1 over s of x in both cases. But because we've done, we've scaled it down, then the probabilities themselves via that, that determined Jacobian term have also to be scaled down. But that's all there is. So we've just replaced, x has gone to this parameter now we have to allow us to scale all of the data points by the same amount. Okay, note that we're allowing each class to have its own parameter vector lambda k, but we're assuming the classes share the same scale parameter s. Okay, so there we go. For the two-class problem, we substitute this expression for the class conditional densities. Yeah, it's generally the same. The main idea is if you take the logarithm of this, what does it look like? And again, and keep in mind, in the PDF version of the book, there's a factor of 1 over s missing. But again, you just take the logs. These terms will cancel out. The 1 over s cancels out. And all that matters for each class that's relevant for us is going to be this. So take the log. There it is. It's linear in the data points. Yeah, then there's other terms determining that depend on the parameters and the class priors. So again, a linear function of x. So just to say that if we look in this particular setting of the exponential family, and we can even add a scaling parameter, we can still get linear decision boundaries. And also, as I said, you can get nonlinear decision. You can also get linear decision boundaries when u of x is not equal to x if you make additional assumptions that cancel out the nonlinear terms in u of x. Okay, good. So I think that is all I want to talk about here. About the generative approach to classification and finding decision boundaries. And next, we're going to be talking about the discriminative approach. So hope you learned some stuff. As always, please just comment below if you agree, disagree, like, dislike, and I hope to see you in the next video. Bye.